Thank you, Naveed, for the kind introduction. It's my pleasure to be here. Good to see a lot of friends here that I haven't seen in a while. Okay, so I'm going to talk about why is RLHF data efficient in policy optimization, and I'll explain what I mean by that. This is joint work with Ihan Du, my postdoc. She's the principal author of the work. Anna Winnicki, my PhD student, and Gal Dalal, who's at NVIDIA, and Shai Manor, who is jointly at Technion and NVIDIA. And I think Shai was John's postdoc, and he's a LIDS postdoc. So there's another LIDS connection to the talk. Okay, so this is the obligatory slide. Reinforcement learning has been widely successful and wildly successful in a number of areas, game playing, robotics, and autonomous driving, and many other places. So at a very high level in reinforcement learning, you have an agent that takes an action. It changes the state of the system. The action changes the state of the system. And then you observe a reward for at this particular state. If this action is taken, this is the reward that you get. And then this information goes back to the agent, and then this process continues, right? To train a reinforcement learning agent, what you have to do is you have to start off with some policy for the agent, meaning that some action that the agent takes at a particular state, and then you learn what is the optimal policy by observing the rewards at each state action pair. Okay? But there are many applications of reinforcement learning where the reward is unknown. It can't even be quantified what it means to get a reward at a particular state, taking a particular action. On the other hand, a human observing this process might be able to give feedback on whether they like what the reinforcement learning agent is doing or doesn't like what the reinforcement learning agent is doing. There are many types of human feedback that can be provided in situations like this. So my interest in this problem started when I talked to two different car companies. One is NVIDIA, and then this another car company that I talked to. And different people use completely different forms of human feedback. One common, this is a major Chinese car company, electric car company. What they do is they have a driver drive a car, okay? And then they use sensors to measure the performance of the driver. So for example, if you go fast within the speed limit, then your reward is high. But if you get too close to another car, then you get your reward gets reduced. And they measure the derivative of acceleration called jerk, which is what basically, if your jerk is 0, you feel a more comfortable ride than otherwise. So they measure jerk, closeness to other cars, the speed of your car, adherence to traffic rules, etc. All of these are measured just based on the sensors that are in the car, and they use the sensor data to evaluate drivers. So they might have like 1,000 people drive their cars, and they might try to figure out the best 50 people based on purely objectively. There's nothing subjective about it, objectively, in the sense of based on just what the measurements that they get. And then these 50 drivers are considered the best drivers, and then you try to do what is called imitation learning, which is a well-studied subject. It's within RL. So you try to design an algorithm that does as well as the best driver, but of course you have to modify things because the best driver may not get into bad situations, so you have to also get some data from the poor drivers to figure out what you would do in those situations and so on. That's one type of reinforcement learning where humans are involved. The second type, this is what the NVIDIA folks in Israel told me, is what they do is that they have an algorithm already. They put a driver in the car. I mean, these are not, when I say autonomous driving, I don't mean fully autonomous driving, autonomous driving features in a car, right? So for example, you might be going on a highway for like 20 minutes. So nothing happens, you're just going on a straight road. And then, so you don't need to ask the human whether they like the ride constantly. So at the end of 20 minutes, you ask them, are you giving a thumbs up or a thumbs down? Or give a rating between 1 and 5 for this portion of the drive. Again, maybe after 20 minutes, maybe you do either a lane change, or let's say you're joining or exiting the highway. So that's a maneuver that might take a couple of minutes. And then at the end of that maneuver, you might ask them, did you like this particular maneuver? And so on. So you take the ride the trajectory and then break it up into small pieces. And when something significant changes at those times, you ask for feedback from the human saying, did you like this part or did you not like this part, and rate it on a scale of 1 to 5 or 0 to 10, whatever. And then they use this information to train a reinforcement learning algorithm. So this is what we are interested in looking at, because this is the problem that they are interested in solving, but this is not something that we have looked at. We have not been able to fully analyze this problem yet. What we did as a preliminary first step is to take an easier kind of model, which is what is used by ChatGPT, for example. So ChatGPT has multiple steps. I'm just these two box steps are what I'm focusing on, and you don't need to read what is in there. Essentially, the idea is that if you ask ChatGPT to write an essay about Abraham Lincoln, for example, it'll write an essay, right? And then if you give the same prompt to it again, it'll write a different essay, because there are some stochastic elements built into it to make it appear to be more human. And then you ask a human which one of these two essays you liked. Okay, so it's sort of from an RL perspective, you can think of it as you're showing two trajectories of a system. By a trajectory, I mean a sequence of state action pairs. And then you ask the question, which one of these two trajectories you like? Okay, and the human then gives some information. And then based on this information, you infer rewards, and I'll tell you how that is done. And once you infer the rewards, you use those rewards to drive your algorithm. Going back, here I said normally in reinforcement learning, you assume that for each state and action, you observe a reward. Since there is no reward in many problems, okay, you just use information that a human provides you to infer or to have a surrogate of a reward for each state action pair. So you can just run regular algorithms like Q-learning or policy gradient or whatever algorithm that you want. Okay. So this is the model that I'm going to focus on. Is basically you're given two trajectories at any time I mean, you can also give 5 trajectories and ask them to rank it, but I'm just going to consider the case of 2 trajectories, ask them to compare and say which one is better. Is the model clear? Or the motivation, I guess. I haven't given the model yet. So the first paper, to the best of my knowledge, on reinforcement learning from human feedback was this paper by Cristiano et al. In 2017. So they considered problems where either the goals are hard to specify, or even for problem where the goals are easy to specify, they just ask the human to tell them whether they, I mean, like you're playing an Atari game or something like that, and you ask an expert, do you like the way this algorithm is playing the game? Okay. So what Cristiano et al. Showed was, for many examples of Atari games and in examples in robotics, they showed that if you just give less than 1% of what you observe an agent doing to a human, that information alone is sufficient to design good algorithms. Okay? The amount of human feedback that you need is relatively small compared to the total amount of data that you need to train a reinforcement learning algorithm. Okay? And here are some pictures. So this orange line is the reinforcement learning. So this is an example where the rewards are somehow known, and if you use human feedback to do this, you don't quite get exactly the same performance, but it's approximately similar, at least after a sufficient amount of time. And similarly, this is another example of something called a beam rider, and this paper has 20, 30 examples like this, where you use human feedback and then you get nearly the same performance, even in situations where the instantaneous reward is known, like in some computer games. They've also show examples in the paper where with human feedback you achieve better performance than otherwise, because humans can somehow figure out a better reward than what is already built into the system. So the question we asked here is, why does RLHF need only a small amount of human data to achieve good performance? And we try to provide an explanation for it from the perspective of policy optimization. Policy optimization is a widely used procedure to train reinforcement learning algorithms. So I'm going to consider policy optimization. Here one could consider other things like Q-learning and so on. Here I'm considering policy optimization, because right now it seems to be the most popular technique to train RL algorithms. Okay, just a small amount of notation. I hopefully won't be using too much of it in any case. So I'm going to consider the discounted MDP setting. So I have a state action, S and A denotes state and the action taken in that state. RSA is an unknown reward function. Normally you assume that when you take a certain action in a certain state, you observe a reward. And here the assumption is that that is unknown, and that's one of the things we want to infer. There is a probability transition matrix with in state S. If you take action A, you move to a new state S prime, and again that is unknown. So that probability transition matrix is unknown. The discount factor, so I'm assuming it's a discounted cost problem, so gamma denotes a discount factor, and there is some fixed initial state S0. This can be modified. Yeah.
Just maybe some philosophical question. I'm trying to see when you are estimating these unknown rewards. So when do we know that we did a good job? Let's say I'm playing chess, right? So I'm looking at the state of the board, and I don't know, like, maybe as an expert, I would know that this, given the state of the board, I'm actually like the board is in my favor. So then I'm trying to see after these things, maybe I'm gonna get to that. Like, how do I know that I did a good job estimating or estimating these reward things? Because in principle they're unknown, we can assign them anything. But I think is there any criteria to figure out if you did a good job?
So it's a very good question. So in a problem where the rewards are truly unknown, the only thing you could do is you try to run this and see if you get a reasonable performance at the end of it. But the way you evaluate it is for problems for which the rewards are already known. Take a MDP, make up your own MDP, for example, and you have a state action. For each state action there is a known reward, okay? But you don't assume that you know it. You just show a human, what the trajectory looks like. I mean, I'll give an example towards the end if I have time. And so you take a known MDP and then ask a human to pretend that they don't know what the actual rewards are and ask them to evaluate the various trajectories if the trajectories have some meaning to the humans, okay? And then in those examples, if you perform well, you know that your algorithm works well. But on examples for which there is really no reward at any state, if you're asking a robot to scramble an egg, ultimately if it scrambles an egg and doesn't spill all over the place, then you know that you've designed a good algorithm. Yeah. And pi of A given S is the probability of taking action A in state S. So I think I'm going to bore you a little bit. So this is the value function is just simply the total accumulated reward starting from an initial state S using policy pi. Q pi is you start with an initial state S and take an initial action A, but after that you use policy pi. That's called the Q function, or the state action value function. This is the state value function. The optimal policy is, of course, pi star, which maximizes B pi, and the Q function under the optimal policy is called, there should be a maximization over pi 2 here. No, this should be maximization over pi not A. Yeah. Okay, so what is policy optimization? Policy optimization is just a approximation to policy iteration. So when I did MDPs in stochastic control in the 1980s, we always assumed everything was known, and then we will take a 5-state MDP and do a homework problem and show that it actually converges. So at that time we were taught policy iteration and value iteration. And policy iteration, so here today what I'm going to talk about is policy iteration. So in policy iteration, let's say you have a Q function, usually start with the policy, but let me just say you start with the Q function. And then what you do is pretend that is a true Q function, and then you take the maximum of that over all possible actions, and then make that the action that you choose. So you choose the A for which this is maximized, you take the probability of that action to be equal to 1. So this is not very well clearly written, but that's what I mean. Basically, take the action A that maximizes this value in state S. And then you evaluate this policy. So you pretend that you know the value function and then come up with a policy, and then you evaluate this policy. It's well known that the Q function satisfies a fixed point equation, which I'm sure most of you know, and then you solve this fixed point equation to evaluate the policy. This is what you would do if you know the MDP. If you know the probability transition matrices, if you know the rewards and everything, then this is one of the two major techniques that one can use. The other one is value iteration. And what policy optimization is, and this particular way of policy optimization is what is also called NPG, or natural policy gradient. It has an interpretation in terms of gradient descent. but I'm not going to give that interpretation. There's a simpler interpretation in terms of approximately solving this maximization. So instead of exactly solving this maximization, I do a softmax here. So the new policy is the old policy multiplied by e raised to the power of eta QSA. So as eta goes to infinity, you will find the true max. Otherwise, it's proportional to this. You have to normalize it to get the probability. Okay? This has the interpretation of gradient descent, but the gradient in gradient descent here, you will be measuring distances in terms of the KL distance. So it's very closely related to mirror descent. So it's not usual gradient descent. It's like mirror descent, and you can interpret NPG in terms of mirror descent. And then what you do is that, so this is the policy improvement step is replaced in policy iteration. Instead of the exact policy improvement, you do approximate policy improvement. And then you collect samples from a trajectory generated by pi and estimate the Q function. Okay, so this is standard policy optimization. And how do you do this? This can be done using TD learning, for example. But in this work, we don't use TD learning because convergence times of TD learning are closely related to mixing times of the Markov chain that you're dealing with. So we use a different procedure to avoid dependence on the policy. Okay, so before I do that, I guess, of course, so to do this, it's impossible to learn the Q function for all state action pairs. So you can only do it up to a function approximation. So what I assume is that for each state action pair, there is a feature vector that is known, okay? And I'm going to assume the Q function is phi transpose theta. It's linearly parameterized, okay? And I'm going to try to find the best Q within this class, okay? And so policy evaluation then boils down to learning the theta, right? And therefore, if I assume Q is theta transpose phi, then, or phi transpose theta, then the same approximate policy improvement can be written as pi a given s multiplied by e raised. So the same, what I've written here, I've just replaced Q by phi transpose theta. Okay, this must all be familiar to most of you. But except, I mean, unless you've seen NPG, you may not have seen this particular version of policy improvement. But there are many other variants of this that look like this. So to actually estimate the policy, what I'm going to do is I'm going to fix a policy. Okay, I'm going to try to minimize the Q function is equal to phi transpose theta. So a natural thing to do is to do something like linear regression. Okay, so to do this, but I need to take an expectation over the state action pair. So I assume the state action pair comes from some row, and I'll talk about what the row is. You just basically sample an initial state from this row, run your policy, add up all the rewards that you get, that gives you the Q function, and then do it again, do it again, do it again, and then you do gradient descent. Okay, and then at the end, to reduce variance, you take an average of your theta estimates. Okay. Okay, I'm going to skip this slide in the interest of time. So that whole procedure that I described works if so you run a policy pi starting from some initial state SIAI, and to figure out what the Q function for it or an estimate of the Q function, you add up all the rewards multiplied by the discount factor, right? But I can't do that if I don't know what the rewards are. So this is the problem. For many problems of interest, example, a robot scrambling an egg, you don't have this. And so the question is, what should you use instead of R of S comma A? That's the question. Okay, is that clear? Okay, so what do I do in that case? So I do what is called reward learning first. So what I'm going to do is I'm going to use a policy, okay? And I'm going to generate trajectories from, let's say you use two policies for simplicity. You use policy 1, generate a trajectory from that policy. Policy 2, generate a trajectory from that policy. Show it to a human and ask which of those two things you like better. And you do this multiple times. You use this information to somehow come up with a model for R, which I'll go through in the next few slides. And then after that, you've learned those rewards. You pretend that those rewards are the true rewards and run policy optimization. Is that clear? So the first step is human comparison. And so there's no, I mean, they're performed sequentially. I mean, this doesn't completely work, but I'll show you a fix for it later on. But at this point, let's just say that you first show lots and lots of trajectories to lots and lots of people, or the same person evaluates lots and lots of trajectories. Do I like this? Do I like this? Do I like this? Or do I like this? And so you show them many pairs of trajectories, and then you have them compare it, and somehow use that information to learn the rewards. Okay, and I'll tell you how that is done. This I know many of you here have even worked on this type of models. So you assume the reward is parameterized also, just like the value function. You assume the reward is of the form phi transpose mu. So now if you give me a trajectory of length h plus 1, the total reward is this, which is a known quantity multiplied by mu. Mu is what is unknown. Okay, so you have to learn mu from comparisons. What do? The most natural thing to do is to assume the Bradley-Terry model. In fact, this is exactly what Cristiano et al. Did. Okay, so they assume the Bradley-Terry model. Under the Bradley-Terry model, you assume, I mean, you don't know this reward. The reward, let's say the reward of trajectory 1 is R1, reward of trajectory 2 is R2. Then you assume that when you show these two trajectories to a person, they'll pick, they'll say that they like trajectory 1 with probability proportional to e raised to the power of R1, and they'll like trajectory 2 proportional to with probability proportional to e raised to the power of R2. So now, basically, if you've gotten lots of such trajectory comparisons, it becomes a straightforward maximum likelihood estimation problem to solve for mu. So I won't belabor that, but basically you need to learn this mu. So you don't know R's, but you have comparisons, and the comparisons you assume are probabilistically given by the Bradley-Terry model. And so therefore, finding mu reduces to a maximum likelihood problem. Okay, we don't have to look at the details of this. And this problem is well studied, for example, and even, I mean, the Bradley-Terry model is an old model, and there's a lot of work on this. But in the context of reinforcement learning, there's a paper by Zhu, Michael Jordan, and Jiantao Zhao, who showed that the MLE estimate of mu minus the true mu weighted by some matrix, I mean, blah, 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 it doesn't, all of these doesn't really matter, but the number of, essentially it says that as the number of comparisons that you give to humans increases, this error goes down. And this is a regularization factor, and this regularization factor, if it's chosen to be 1 over MHF, then the whole thing will go to 0 at rate 1 over MHF. Okay, so basically what this is saying is that as it's an obvious statement, as you keep increasing the number of human comparisons that people do, the comparisons that humans do, then of course the error in this MLE estimator is going to go down. But the problem for us is that you need to figure out how the error here propagates in this algorithm, because there is going to be an error in the reward model, and you have to figure out how that error propagates here, and so that would determine how long you have to, how many human comparisons you have to do. Okay?
So question.
Yeah.
In this diagram, both things are at the same time scale, the theta estimate and the mu estimate?
No. So the mu estimate is done here first, and then you run this thing. These two are completely separated. Yeah. I'll talk about why that is not good, but at this point, we'll just, for simplicity, that's the easiest way to explain my result, and then and yeah. So that's what we'll do. Okay. Okay. So the question is, so this is just quickly to recap. So I'm estimating mu from here, sticking it in here, and then do standard policy optimization where I do an approximate policy improvement, and either TD learning, I mean, this is the reason we did something else, was for mathematical convenience, but it can be TD learning here, for example. So the main result, hopefully this slide will convey most of the what I want to say, is that if you run this algorithm for t iterations, I'm going to do t iterations of policy improvement here. Okay, if I run this algorithm for t iterations, and within each iteration I do MSGD is the notation I'm going to use for the number of SGD updates that I do to do policy evaluation. And if I do MHF human comparisons, then the difference between the true value function and the value function of the policy that we output decays like this. I mean, there's going to be a bias that cannot be gotten rid of. That is the bias due to function approximation. So if your function approximation is not accurate, there's nothing you can do about it, and that is a bias due to that. But the rest of it decays like this. So as a function of t, the function of number of policy improvement steps that you do, the error goes down as 1 over square root of t, and the number of SGD steps that you do within each iteration, it goes down as 1 over m power 4, and number of human feedback comparisons also go over 1 over m power 4. So one of the interesting sort of complicated things we had to do was to take the result by Zhu, Jordan, and Zhao, and basically propagate that through the policy optimization phase and figure out what the error in the outer part of this, how does it contribute to the overall error. That's the most significant amount of work in the paper. Yeah?
Can you give some intuition why you're getting sort of an unusual 1/4 rate in the terms?
Yeah, so it's so there are many terms. So basically there is so there is Q SA. I'm trying to estimate, and I'm trying to estimate this as theta transpose phi SA. But when I do this, I don't have access to the true R. I have access to R hat, and so I sort of have let's see, Q R hat. So to do all of this, so I have to bound this. I think there's one more thing that we also have to bound, and we couldn't directly bound all of this. So we just basically we got a 1 over m power half, and then had to get a square root of that to get the result. So let me see, what was the? So there were 3 things. So we had actually, we had something like this, a minus b squared plus b minus, a term like this. I'm not remembering it correctly. Somehow there was a term like this, and then we had to write it in terms of a minus c square and some other term, b minus d square. I don't know. It's 1 over. So this is 1 over m power half is for the norm. Yeah, what is the identity we used? It'll come to me. I'll tell you. So this is, so basically we're using prior work to estimate this error, and there's one more error that I'm not remembering now. So this QR as a function of R hat. So this is a standard error, right? This is from TD learning kind of thing, right? Let's say we use TD learning. That's what this error. I mean, in this case, we are using SGD. So this error is much harder to quantify. And what did we? So what we did was that. So it is this error that's complicated. That is basically what was pointing out. But I can't remember how to. I mean, I don't remember how we bounded that. It'll come. I'll tell you at the end of the seminar if I'm right. Okay. Yeah. So it becomes 1 over mgd power 1/4, and yeah. So basically, what this is saying is that. So what is the overall sample complexity? The overall sample complexity is t times msgd, because within each iteration, with each value improvement step, we are using we are doing msgd steps of sgd, so it's t times msgd, and we are adding human feedback at the beginning. So the total number of samples we have is T MSGD plus MHF because of human feedback. If we did not have human feedback and knew the reward, it'll be T MSGD. And the number of extra queries that we are doing in this case, when we are doing RLHF, it is order of MHF. So basically, overall, the idea is that the extra amount of samples that you need, the ratio of that is MHF divided by MSGD times T, and this is approximately 1 over T because these two are of the same order. So in partial answer to Martin's question, suppose this was m power half, like in the Jordan result. Suppose it doesn't get worse. It can only improve our result. Do you see what I'm saying? So this is a crude upper bound is what I would say. So it can only improve our result. Yeah. The point here is that the fact that MSGD and MHF affect the error in the same order is important, meaning that, well, as I said, if MHF actually affects in a better order, then it's even better. But if it had turned out that if at least, let's say, we couldn't bound it and we came up with some result like 1 over m power 1/8, then the dependence on the human feedback comparison would not be, there'll be more of a dependence on the human feedback comparison. It won't go down as like 1 over t. Is that clear? Basically, what I'm saying is that if you think about it, let's say you want an error of 3 epsilon here. So you make this less than epsilon, make this less than epsilon, makes this less than epsilon, right? And then if you compare it, then basically this is in the outer loop, whereas these two get multiplied with each other. That is basically the reason why it works. This is the high level intuition. Yeah?
So let's say human feedback is a subjective feedback. You get a scale from 1 to 10.
Okay, that's a different type of human feedback. Here I'm just comparing trajectories and saying that do you like this or that, that's it.
So it's a binary feedback.
It's binary feedback.
But I'm giving an example, 1 to 10 we get feedback. There's an element of subjectivity there. If you take that and turn it into binary feedback, you might lose some information.
Yeah.
And if you just take it with a grain of salt, there is an
Yeah.
element. So how do you decide what level of
That's a question that you have to assume some model as to why people are giving. Even here, I'm going to
search like take that 1 to, let's say 1 to 16. You have 4 bits for it, and then you start dropping, and make it coarser grain. How do you do it?
That I don't know. I mean, I don't know the answer to that. So here we're assuming it's binary feedback. You could have, as I said, that's also a type of feedback that some car companies use. I don't know how they do it. So this is just the binary feedback case that we've looked at. Yeah.
I think if I can interject a concern with that kind of feedback would be calibration. If you have many people,
right.
I use my 1 to 10 scale differently than you, then we can't really compare our data. Whereas if we all do binary comparisons, and
it's much easier.
leave the Bradley-Terry model, then you can lump all the data together. So.
But the question is that you have 4 bits for feedback versus a single bit. Maybe 2 bits is better.
No, but you shouldn't collect feedback like that as part of the point. I mean, what Martin's saying is that you should not do this 1 to 5 or 1 to 10 thing because that's subjective, more subjective than comparisons.
But I mean, the notion of jerkiness that we talked about
right.
is subjective. I'm writing.
It is subjective in the sense that it depends on the human, and we partially account for it in this Bradley-Terry model. Who knows whether the Bradley-Terry model is accurate or not? That's correct. Yeah.
Thank you.
So there is one piece of work where people assume that the total sum of rewards for a trajectory is the feedback that the humans give you. I mean, but there the assumption is that they somehow magically know the sum of the rewards and then they tell you that. If you do that, yeah, then actually it's an actual score, but whether humans can actually tell that is a tricky thing. Yeah. Yeah.
Just to take the other tangent, so suppose the feedback is not comparison, but just it's the sum of the rewards plus some noise.
Mm-hmm.
So the same conclusion holds true that you only need a few of those.
I think so, because that would be an easier regression problem probably, right? It's even easier than the Bradley-Terry model. You're just trying to fit a straight line to find the theta, right? Should be, I think, should be easier. Yeah. Yeah, that's a good question, yeah. If you add noise to it, then it would just be, you can just solve it as a regression problem. Okay, So one limitation of this approach is I just didn't put the constants in. That is the limitation. And the constants depend on certain ratios. Basically, it depends on, let's say, there's something called the state visitation distribution. So if you look at, if you take in reinforcement learning with discounted reward, you can think of alpha as the probability with which you're stopping or continue. Alpha is the probability with which you're continuing. And using this notion, there is something called, so you can look at the probability distribution of how often you visit how often you get to a certain state. Okay, the constants depend on the ratio of some covariance matrix, which further depends on this state visitation distribution of the optimal policy versus the covariance matrix of the policy that you are computing at time t. And it depends on this ratio, and there's no way to bound this ratio. At least I don't know how to bound this ratio. We don't know how to bound this ratio. So this could be very large. And so the idea is that coverage is a problem. Basically, what you have to do is you have to make sure that the number of times you visit the state action pair in the optimal policy versus the policies that you're getting through policy optimization, they should be somewhat aligned. Otherwise these ratios could be very, very large. So there is a technique to, so now I'll add an outer loop. The outer loop, this idea is due to, not in the context of RLHF, but in standard RL. This is an idea that was proposed by Agarwal et al. To encourage exploration. So what they do is that they look at all the previous policies that you have obtained, and then take the average of them and use that as the policy to explore. Okay, so when you do policy optimization, they explore the state space using a policy, not the current policy, because the current policy, if you're going towards the optimal policy, it could become deterministic, and so therefore you won't be exploring the state space. Is that clear? So if the policy becomes deterministic, you're not going to be exploring the state space, and so therefore you may not be able to visit all state action pairs. So what they propose is an idea where they showed that if you use this, if you use the average of all the policies that you've seen so far, that will still be probabilistic, and it gives you enough exploration. So basically, we're using this idea in the context of. Let me just see how much time I have. In the context of our problem, so I'll just skip through some of these slides. And then what we show is that even including that, we get similar results, but now there is a dependence of 1 over n on the outer loop. So we get rid of those constants that depend on the ratio of the probability distributions of the optimal policy to your policy. Okay, so that is basically the more general result. So it avoids dependence on coverage factors, and the same conclusion. So in the final part of our work, so we assume parameterized forms here, right? We assume that it's of the form phi transpose theta. Okay, it's linear is what we assume. So now we are using a neural network. So you can, to the neural network, you can directly feed the state action pair, or if you know of some features, you can feed the phi of SA. And then you pass it through okay, all the analysis is for single hidden layer neural network, and any of you who have seen the NTK approximation know why this is, because that's how we can analyze. So for a single hidden layer neural network, so we no longer have to assume this parametric model like this, and you can assume that the Q function and both the reward and the Q functions have to be learned approximately. I mean, it can be learned through a neural network, and of course, the neural networks can approximate. If M is sufficiently large, it can approximate any continuous function over a compact set. So you have better representation capability than just a linear network. And then here we get an even worse result. We get 1 over m power 160, where m is the size of the neural network. So the dependence on the size of the neural network. So here, I guess. Martin asked why you get m power 1 over 4, m power 1 over 16. There are many reasons you get where it gets worse. Yeah?
Can I ask one question about the feedback loop?
Okay.
So for the like random draw the two trajectories from all the?
No, it's not random draw. Okay, so yeah, I skipped over a slide. So what I'm going to assume here is that to avoid correlations, what I'm going to do is I have something called a baseline policy. I'm always comparing the new policy's trajectories to a baseline policy. Thank you. Yeah. There's a baseline policy which is assumed to be sufficiently rich. I mean, which provides, and I'm always comparing to that. Otherwise, the correlation, so I'm not comparing, let's say at time step t, you generate a policy pi t, and time step t plus 1, you generate a policy pi t plus 1. If you start comparing those two things, then there's so much correlation that we're unable to analyze it. So we assume a fixed baseline policy, and every time you get a new policy, you generate trajectories from the two of them, and they compare. And then you do this comparison many times. Yeah. Here, the reason we get 1 over m power 1 over 16 is basically we assume that the function that we are, that the Q function and the reward function belong to some RKHS, okay? And in particular, the NTK RKHS. And then you're approximating the kernel by a neural network. And further, the neural network parameters change over time. So I don't know. So there are too many things that are deviating from the original RKHS. Adding all of that together, it gives a 1 over m power 1 over 16. I don't know if this is optimal or not. I have no idea. But it just, all I can say at this point is that it goes to 0 as m goes to infinity, but it goes to 0 at a very poor rate. Of course, this is a single layer neural network. So if you use deep neural networks, it has better approximation capabilities. Probably it will perform much better, but we don't have the tools to analyze it yet. I mean, meaning means the whole community doesn't have tools to analyze deep neural networks very well and how they train under SGD and so on. So this is why that result is 1 over m power 1/16. So I guess in this, and again, I guess in answer to your question, we take an MDP, which is known, okay, and we pretend that there is a human that gives feedback based on the Bradley-Terry model. So we haven't applied this to any real robotics examples or not. So in this particular case, we know what the reward for each trajectory is, and then when we compare two trajectories, we assume that the yes or no, or I prefer 1 versus 2, comes from the Bradley-Terry model. I guess on the other hand, Cristiano has some examples where nothing is known and so on, but we haven't done those experiments yet. So for this problem, surprisingly, the results match quite closely to theory. So our algorithm, so if you run the algorithm for 50 iterations of policy improvement, the number of queries, extra queries that we need for human feedback is like 0.962%. Whereas if you increase that to 100, it is 490, almost exactly half, and then to 200 it further divides. So this 1 over t seems to be reasonably correct, but of course we are not actually having humans compare, so I don't know how it will be in that case. So I think I'm going to conclude here. So hopefully there is some insight into why RLHF is efficient, and I'm hoping that this model can be somehow extended to look at more complicated models of human feedback. Like I said earlier, trajectory comparisons are not the only things that people do. As I said, thumbs up, thumbs down is another very popular form of feedback that actually companies employ. But the problem there is that in a single trajectory, you get lots and lots of feedback. So there's correlation, and you have to assume a model for thumbs up, thumbs down, and we are still working on it in collaboration with Gal and Shai. And the other interesting thing is that, as I mentioned, there is this dependence on what is called coverage. The constants, when I just have this single human feedback step followed by policy optimization, mathematically at least the results don't look very good. So we added this outer loop, and that's another innovation in the paper. And as I said, ongoing work is to understand how to incorporate other forms of human feedback. Okay, thank you.